Benzene is an important organic chemical compound with the chemical formula C6H6. Its molecule is composed of 6 carbon atoms joined in a ring, with 1 hydrogen atom attached to each carbon atom. Because its molecules contain only carbon and hydrogen atoms, benzene is classed as a hydrocarbon. Benzene is a natural constituent of crude oil, and is one of the most elementary petrochemicals. Benzene is an aromatic hydrocarbon and a second N, an allene, a cyclic hydrocarbon with a continuous pi bond. It is sometimes abbreviated PHH. Benzene is a colorless and highly flammable liquid with a sweet smell. It is mainly used as a precursor to heavy chemicals, such as ethylbenzene and cumena, which are produced on a billion kilogram scale. Because it has a high octane number, it is an important component of gasoline, comprising a few % of its mass. Most non-industrial applications have been limited by benzene's carcinogenicity. History. Discovery. The word benzene derives historically from gum benzoin, an aromatic resin known to European pharmacists and perfumers since the 15th century as a product of Southeast Asia. An acidic material was derived from benzoin by sublimation, and named flowers of benzoin, or benzoic acid. The hydrocarbon derived from benzoic acid thus acquired the name benzene, benzol, or benzene. Michael Faraday first isolated and identified benzene in 1825 from the oily residue derived from the production of illuminating gas, giving it the name bicarbonate of hydrogen. In 1833, Elhard Mitscherlich produced it via the distillation of benzoic acid and lime. He gave the compound the name benzene. In 1836, the French chemist Auguste Laurent named the substance phene. This is the root of the word phenol, which is hydroxylated benzene, and phenol, which is the radical formed by abstraction of a hydrogen atom from benzene. In 1845, Charles Mansfield, working under August Wilhelm von Hofmann, isolated benzene from coal tar. 4 years later, Mansfield began the first industrial-scale production of benzene, based on the coal tar method. Gradually the sense developed among chemists that substances related to benzene represent a diverse chemical family. In 1855, Hofmann used the word aromatic to designate this family relationship, after a characteristic property of many of its members. In 1997, benzene was detected in deep space. Ring formula. The empirical formula for benzene was long known, but its highly polyunsaturated structure, with just 1 hydrogen atom for each carbon atom, was challenging to determine. Archibald Scott Cooper in 1858 and Joseph Loschmidt in 1861 suggested possible structures that contained multiple double bonds or multiple rings. But too little evidence was then available to help chemists decide on any particular structure. In 1865, the German chemist Friedrich August Kekulé published a paper in French suggesting that the structure contained a 6-membered ring of carbon atoms, with alternating, single and double bonds. The next year he published a much longer paper in German on the same subject. Kekulé used evidence that had accumulated in the intervening years, namely, that there always appeared to be only 1 isomer of any monoderivative of benzene, and that there always appeared to be exactly 3 isomers of every disubstituted derivative, now understood to correspond to the ortho, meta, and para patterns of RNA substitution, to argue in support of his proposed structure. Kekulé's symmetrical ring could explain these curious facts, as well as benzene's 1:1 carbon-hydrogen ratio. The new understanding of benzene, and hence of all aromatic compounds, proved to be so important for both pure and applied chemistry that in 1890 the German Chemical Society organized an elaborate appreciation in Kekulé's honor, celebrating the 25th anniversary of his first benzene paper. Here Kekulé spoke of the creation of the theory. He said that he had discovered the ring shape of the benzene molecule after having a reverie or daydream of a snake seizing its own tail. This vision, he said, came to him after years of studying the nature of carbon-carbon bonds. This was 7 years after he had solved the problem of how carbon atoms could bond to up to 4 other atoms at the same time. It is curious that a similar, humorous depiction of benzene had appeared in 1886 in the Berichte der Deutschen chemischen Gesellschaft, a parody of the Berichte der Deutschen chemischen Gesellschaft, only the parody had monkeys seizing each other in a circle, rather than snakes as in Kekule's anecdote. Some historians have suggested that the parody was a lampoon of the snake anecdote, possibly already well known through oral transmission even if it had not yet appeared in print. Kekule's 1890 speech in which these anecdotes appeared has been translated into English. If the anecdote is the memory of a real event, circumstances mentioned in the story suggest that it must have happened early in 1862. The cyclic nature of benzene was finally confirmed by the crystallographer Kathleen Lonsdale in 1929. Nomenclature. The first use of the prefixes ortho, meta, para to distinguish di-substituted benzene derivatives was by the German chemist Wilhelm Korner in 1867, however, he did not use the prefixes to distinguish the relative positions of the substituents on a benzene ring. It was the German chemist Karl Graber who, in 1869, first used the prefixes ortho, meta, para to denote specific relative locations of the substituents on a di-substituted aromatic ring. In 1870, the German chemist Victor Meyer first applied Graber's nomenclature to benzene. Early applications in the 19th and early 20th centuries, benzene was used as an aftershave lotion because of its pleasant smell. Prior to the 1920s, benzene was frequently used as an industrial solvent, especially for degreasing metal. As its toxicity became obvious, benzene was supplanted by other solvents, especially toluene, which has similar physical properties but is not as carcinogenic. In 1903, Ludwig Roselius popularized the use of benzene to decaffeinate coffee. This discovery led to the production of Sanka. This process was later discontinued. Benzene was historically used as a significant component in many consumer products such as liquid wrench, several paint strippers, rubber cements, spot removers and other hydrocarbon-containing products. Some ceased manufacture of their benzene-containing formulations in about 1950. While others continued to use benzene as a component or significant contaminant until the late 1970s when leukemia deaths were found associated with Goodyear's plyo-film production operations in Ohio. Until the late 1970s, many hardware stores, paint stores, and other retail outlets sold benzene in small cans, such as quart-sized, for general-purpose use. Many students were exposed to benzene in school or university courses while performing laboratory experiments with little or no ventilation. In many cases, this dangerous practice has been almost totally eliminated. Occurrence trace amounts of benzene are found in petroleum and coal. It is a byproduct of the incomplete combustion of many materials. For commercial use, until World War II, most benzene was obtained as a byproduct of coke production for the steel industry. However, in the 1950s, increased demand for benzene, especially from the growing polymers industry, necessitated the production of benzene from petroleum. Today, most benzene comes from the petrochemical industry, with only a small fraction being produced from coal. Structure. X-ray diffraction shows that all 6 carbon-carbon bonds in benzene are of the same length, at 140 picometers. The CC bond lengths are greater than a double bond but shorter than a single bond. This intermediate distance is consistent with electron delocalization. The electrons for CC bonding are distributed equally between each of the 6 carbon atoms. Benzene has 6 hydrogen atoms, fewer than the corresponding parent alkane, hexane. The molecule is planar. The mode description involves the formation of 3 delocalized pi orbitals spanning all 6 carbon atoms, while the VB description involves a superposition of resonance structures. It is likely that this stability contributes to the peculiar molecular and chemical properties known as aromaticity. To accurately reflect the nature of the bonding, benzene is often depicted with a circle inside a hexagonal arrangement of carbon atoms. Derivatives of benzene occur sufficiently often as a component of organic molecules that there is a Unicode symbol in the miscellaneous technical block with the code U plus 232C to represent it with 3 double bonds, and U plus 23E3 for a delocalized version. Benzene derivatives. Many important chemical compounds are derived from benzene by replacing one or more of its hydrogen atoms with another functional group. Examples of simple benzene derivatives are phenol, toluene, and aniline, abbreviated PHO, PHME, and PHNH2, respectively. Linking benzene rings gives biphenyl C6H5C6H5. Further loss of hydrogen gives fused aromatic hydrocarbons, such as naphthalene and anthracene. The limit of the fusion process is the hydrogen-free allotrope of carbon, graphite. In heterocycles, carbon atoms in the benzene ring are replaced with other elements. The most important derivatives are the rings containing nitrogen. Replacing one CH with N gives the compound pyridine, C5H5N. Although benzene and pyridine are structurally related, benzene cannot be converted into pyridine. Replacement of a second CH bond with N gives, depending on the location of the second N, pyridazine, pyrimidine, and pyrazine. Production. 4 chemical processes contribute to industrial benzene production: catalytic reforming, toluene hydroalkylation, toluene disproportionation, and steam cracking. According to the ATSDR toxicological profile for benzene, between 1978 and 1981, catalytic reformats accounted for approximately 44 to 50% of the total U.S. benzene production. Catalytic reforming and catalytic reforming, a mixture of hydrocarbons with boiling points between 60 to 200 degrees Celsius is blended with hydrogen gas and then exposed to a bifunctional platinum chloride or rhenium chloride catalyst at 500 to 525 degrees Celsius and pressures ranging from 8 to 50 atmospheres. Under these conditions, aliphatic hydrocarbons form rings and lose hydrogen to become aromatic hydrocarbons. The aromatic products of the reaction are then separated from the reaction mixture by extraction with any one of a number of solvents, including diethylene glycol or sulfolane, and benzene is then separated from the other aromatics by distillation. The extraction step of aromatics from the reformate is designed to produce aromatics with lowest non-aromatic components. Recovery of the aromatics, commonly referred to as BTX, involves such extraction and distillation steps. There are a good many licensed processes available for extraction of the aromatics. In similar fashion to this catalytic reforming, UOP and BP commercialized a method from LPG to aromatics. Toluene hydroalkylation. Toluene hydroalkylation converts toluene to benzene. In this hydrogen-intensive process, toluene is mixed with hydrogen, then passed over a chromium, molybdenum, or platinum oxide catalyst at 500 to 600 degrees Celsius and 40 to 60 atmospheres pressure. Sometimes, higher temperatures are used instead of a catalyst. Under these conditions, toluene undergoes dealkylation to benzene and methane. C6H5CH3 plus H2C6H6 plus CH4. This irreversible reaction is accompanied by an equilibrium side reaction that produces biphenyl at higher temperature. 2C6H6H2 plus C6H5C6H5 if the raw material stream contains much non-aromatic components. Those are likely decomposed to lower hydrocarbons such as methane, which increases the consumption of hydrogen. A typical reaction yield exceeds 95%. Sometimes, xylenes and heavier aromatics are used in place of toluene, with similar efficiency. This is often called on-purpose methodology to produce benzene, compared to conventional BTX extraction processes. Toluene disproportionation, where a chemical complex has similar demands for both benzene and xylene, then toluene disproportionation may be an attractive alternative to the toluene hydride alkylation. In the broad sense, two toluene molecules are reacted and the methyl groups rearranged from one toluene molecule to the other, yielding one benzene molecule and one xylene molecule. Given that demand for paraxylene substantially exceeds demand for other xylene isomers, a refinement of the TDP process called selective TDP may be used. In this process, the xylene stream exiting the TDP unit is approximately 90% paraxylene. In some current catalytic systems, even the benzene to xylenes ratio is decreased when the demand of xylenes is higher. Steam cracking. Steam cracking is the process for producing ethylene and other alkenes from aliphatic hydrocarbons. Depending on the feedstock used to produce the olefins, steam cracking can produce a benzene-rich liquid byproduct called pyrolysis gasoline. Pyrolysis gasoline can be blended with other hydrocarbons as a gasoline additive, or routed through an extraction process to recover BTX aromatics. Other methods, although of no commercial significance, many other routes to benzene exist. Phenol and halobenzenes can be reduced with metals, for example, benzoic acid and its salts undergo decarboxylation to benzene. Via the reaction, the diazonium compound with hypophosphorus acid aniline gives benzene. Trimerization of acetylene gives benzene. Uses. Benzene is used mainly as an intermediate to make other chemicals, above all ethylbenzene, cumeno, cyclohexane, nitrobenzene, and alkylbenzene. More than half of the entire benzene production is processed into ethylbenzene, a precursor to styrene, which is used to make polymers and plastics like polystyrene and EPS. Some 20% of the benzene production is used to manufacture cumeno, which is needed to produce phenol and acetone for resins and adhesives. Cyclohexane consumes California 10% of the world's benzene production. It is primarily used in the manufacture of nylon fibers, which are processed into textiles and engineering plastics. Smaller amounts of benzene are used to make some types of rubbers, lubricants, dyes, detergents, drugs, explosives, and pesticides. In 2013, the biggest consumer country of benzene was China, followed by the USA. Benzene production is currently expanded in the Middle East and in Africa, whereas capacities in Western Europe and North America stagnate. Toluene is now often used as a substitute for benzene, for instance as a fuel additive. The solvent properties of the two are similar, but toluene is less toxic and has a wider liquid range. Toluene is also processed into benzene, component of gasoline. As a gasoline additive, benzene increases the octane rating and reduces knocking. As a consequence, gasoline often contained several percent benzene before the 1950s, when tetraethyl lead replaced it as the most widely used anti-knock additive. With the global phase-out of leaded gasoline, benzene has made a comeback as a gasoline additive in some nations. In the United States, concern over its negative health effects and the possibility of benzenes entering the groundwater have led to stringent regulation of gasoline's benzene content, with limits typically around 1%. European petrol specifications now contain the same 1% limit on benzene content. The United States Environmental Protection Agency introduced new regulations in 2011 that lowered the benzene content in gasoline to 0.62%. Reactions. The most common reactions of benzene involve substitution of a proton by other groups. Electrophilic aromatic substitution is a general method of derivatizing benzene. Benzene is sufficiently nucleophilic that it undergoes substitution by acylium ions and alkyl carbocations to give substituted derivatives. The most widely practiced example of this reaction is the ethylation of benzene. Approximately 24,700,000 tons were produced in 1999. Highly instructive but of far less industrial significance is the Friedel-Crafts Alkylation of benzene using an alkyl halide in the presence of a strong Lewis acid catalyst. Similarly, the Friedel-Crafts acylation is a related example of electrophilic aromatic substitution. Sulfonation, chlorination, nitration using electrophilic aromatic substitution. Many functional groups are introduced onto the benzene framework. Sulfonation of benzene involves the use of oleum, a mixture of sulfuric acid with sulfur trioxide. Sulfonated benzene derivatives are useful detergents. In nitration, benzene reacts with nitronium ions, which is a strong electrophile produced by combining sulfuric and nitric acids. Nitrobenzene is the precursor to aniline. Chlorination is achieved with chlorine to give chlorobenzene in the presence of a catalyst such as aluminium trichloride. Hydrogenation. Via hydrogenation, benzene and its derivatives convert to cyclohexane and derivatives. This reaction is achieved by the use of high pressures of hydrogen at high temperatures in the presence of a finely divided nickel, which serves as a catalyst. In the absence of the catalyst, benzene is impervious to hydrogen. This reaction is practiced on a very large scale industrially. Metal complexes. Benzene is an excellent ligand in the organometallic chemistry of low-valent metals. Important examples include the sandwich and half-sandwich complexes, respectively, Cr2 and RuCl2.